Okay, sorry about the interruption. Let's continue this lecture. This is a continuation of Lecture 1 for Biology 106, summer of 2014. So, dehydration then, not where we're losing fluid like through hemorrhage or through a terrible burn or chronic diarrhea, but instead you're simply not getting enough fluid into your body. So again, this would be from a lack of drinking water. This could be from diabetes because you're having polyuria. This could be from diabetes insipidus, this condition where there's a hyposecretion of ADH, where you simply do not make ADH. So if your body cannot make ADH or doesn't respond by making ADH, then you would be urinating constantly. And people with diabetes insipidus will urinate 30 or more liters every day. And they are constantly drinking and constantly urinating to make up for this hormonal imbalance. Or profuse sweating, or a person who is over-prescribing or overusing diuretics. Again, infants are far more vulnerable to dehydration than adults simply because they have a higher metabolic rate. Therefore, they need more control of getting rid of those metabolic acids. But their kidneys are not as good at concentrating urine. And so there's just a lot of reasons why infants are more prone to dehydration than an adult. And dehydration is going to affect all fluid compartments across the entire body would be lacking. So here's something that you've probably experienced. So what happens when you walk outside and it's really, really cold? Well, you know that the blood vessels toward the surface of your body are going to vasoconstrict, and that's going to drive all that blood away from the surface of your skin to the core. So what's going to happen to your blood pressure? Yeah, you're right. Your blood pressure is going to increase because you have taken all that blood from the periphery and you've sent it away and toward the center of the body. So that's going to effectively raise your blood pressure. Now, recall back from that flow chart that when the blood pressure is increased, it inhibits ADH. But there's another hormone that you need to know about that is going to work in the opposite way, and that is this one, atrial natriuretic peptide. You'll see it abbreviated as ANP, or you'll see it as ANH. And atrial natriuretic peptide, as the name suggests, is being made and secreted by the atrial cells. So this is coming from the heart, from the atrium. It has to do with natriuretic. Remember, natrium is Latin for sodium, Na. So this is a hormone that is going to have something to do with the heart and sodium. Well, what happens is that as the blood pressure increases, the atria are recognizing that increase. They're being stretched, and as a result, they're releasing these ANP molecules. Well, ANP then travels to the kidney, and as you would expect, the kidney is now going to increase its output to, again, reduce the blood volume and reduce the blood pressure. Okay? So you've got ADH and ANP, two hormones that are helping to regulate your blood pressure. One released by the hypothalamus and the posterior pituitary, the other released by the heart itself. So imagine this. You go outside. It's cold. And all of a sudden, you have to go to the bathroom, don't you? That's exactly what's going on, right? You just walked outside. All of your blood was shunted from your external periphery to the internal. Your blood pressure goes up. Your heart says, wait a second, this pressure is more than I want right now. Sends out ANP and tells the kidneys to get busy to urinate. Right? We've all had that experience. And probably it always happens when you just got the snowsuit on and you're all bundled up, and all of a sudden you have to go to the restroom. Well, now you understand the hormone and the physiology behind that. Now, what else would happen? So you're in cold weather, and it's going to cause both a urinary loss of fluid because your kidneys are going to be activated. It's also going to cause a more fluid loss from your respiratory system because, as the previous slide told us, cold air is drier, and cold air, therefore, will also cause you to increase your respiratory water loss. So it's cold outside, you're blowing off more water, you're losing more moisture, and your kidneys are being activated through the atrial natriuretic peptide. And so as a result, you're becoming a little bit more hypovolemic. So you're becoming a little bit more hypovolemic as a result. Well, what else could go on? Well, what if you're outside and you're already a little bit hypovolemic and now you're going to begin to exercise? Well, that's going to dilate your blood vessels and to your skeletal muscles, and that's going to even reduce more blood flow to your brain. And so you could experience some fatigue or fainting or weakness by going outside and doing more activity than what you're accustomed. Now, again, you can train your body to adapt to this, but I wouldn't recommend going outside in minus 20-degree weather and trying to exercise without expecting some of these symptoms. Now, you can also become dehydrated, like I mentioned, by excessive sweat. So let's just take a look at this. We get this. We sweat, therefore we're losing water. And that sweat is produced by filtration of the capillaries. As a result, the blood volume will drop, pressure will drop, osmolarity will rise, and the blood will absorb that tissue fluid to replace this loss. And so we can see that here in this diagram. The body is going to capture fluid from the interstitial fluid to replace what's being left or what's being lost through the sweating. Now, that's what happens when we lose fluid. What happens if we have fluid in excess? Well, it's not quite as common a problem. There used to be those crazy radio contests where people would be caller number 9 and then go down on a Saturday and be forced to drink a gallon of water every 10 minutes until the last person standing won the car. People die from those things because if you're taking in that much fluid, well beyond what your body needs, yes, your kidneys will be very good initially at taking care of the excess, right? But if you have any kind of renal failure at all, then this can be a real problem. Or if your body, for some reason, can't deal with this excessive intake. Again, it's not as common because not many people would choose to drink. But when you got a gun to your head, and you're trying to get this car, and people were drinking too much, then there can be some real problems. So what could happen here is there could be a volume excess of fluids, and in this case, again, you could have a renal failure such that your body is not responding like it should, or there could be a hypotonic hydration, that is pure water intoxication, and you're getting more water than sodium. Your fluid becomes hypotonic, or sorry, your extracellular fluid becomes hypotonic. And recall what happens to cells when they're put into a hypotonic environment. They swell. And this can lead to cerebral edema, pulmonary edema, and death in the extreme situation. So again, this is those crazy contests where people are just drinking water, 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 and it could cause some cerebral edema, pulmonary edema, or if the body wasn't able to deal with that, there's some sort of kidney problems as well. It could definitely be a deadly combination. So let's just take a look at this graph and make sense of this. I told you that the average person is taking in about 2,500 mils of water every day, right? So here's that normal range basically. And within the normal range, look up here at the blood volume. Essentially, it's a straight line, isn't it? So what that tells us is that within this range, within this normal range, that the body has no trouble with this much fluid coming in every day to maintain a flat line on your blood volume. And even if you drink way more every day, 3 to 8 liters, look at this, the kidneys are still able to deal with this, and you're still going to have a flat line. Okay? But uh-oh, look what happens though if you are not drinking enough water. So we look, someone's drinking less than, 1 liter of water a day. Well, look what happens. Very quickly, there is hypovolemia going on and death. So if your blood volume is down around 3 liters, you're dead. Okay? So it's very, very important that we're getting enough water. There used to be a day when hunger and water strikes were very common by prisoners to make some political statement. And when a person went on a hunger strike, it could go on and on and on, days, even weeks, before a person would die from not eating. But if that person decided to instead go on a liquid strike or a water strike, you know they're going to be dead in less than a week. So we cannot live without water. Now, what happens if you start getting in too much fluid? Well, that fluid can sequester, right? Fluid sequestration is a fancy way of saying water is being captured in an area more than it should. Okay, excess accumulation of the fluid. So if we're getting this is going to be basically edema of some sort, isn't it? Some sort of accumulation of fluid. Now, total body water could be overall normal, but for some reason there's a point at which the volume of circulating blood drops, and that can cause the circulatory shock. So if too much fluid is going to one area, you may not have enough blood volume, and that could cause circulatory shock. Now, in the most common form, if you have some sort of fluid sequestration, you're going to have edema, right? You're going to have an accumulation of fluid where it shouldn't be. Now, what can cause this? This could be caused by hemorrhage. So you're bleeding out internally, and that fluid is accumulating in a place where it shouldn't be. Now, keep in mind that blood is pooling and is being lost to the circulation, so you're becoming hypovolemic as well. And this fluid can accumulate around the pleura. And this can lead to fluid buildup in the pleura, difficulty breathing, difficulty with gas exchange, and this certainly can be brought on by chronic bronchitis and other lung infections. Now, so we're talking about how water moves from one compartment to another, right? That's been our conversation here. Well, and I told you at the very beginning that sodium and other electrolytes are the key to understanding this movement of water. So it's very important that we have, for our overall metabolism, that we have the proper compartmentalization of these electrolytes. And we're going to see that the proper placement of these electrolytes is going to give us, on our cell membranes, a strong electrical potential. That is, there's going to be a difference in the charge on the inside and outside of cells. This will become absolutely critical when we discuss action potentials and muscle contraction, because both neurons and muscle are excitable tissues. That means they respond to electrical changes, and we'll be understanding this in greater detail in the coming days. This change in electrolytes has a big difference on the osmolarity of fluids and completely controls the distribution and water content of your compartments. Now, the major cations are sodium, potassium, calcium, and protons, hydrogen. Now, what does cation mean? That's right, cations are the positively charged ions. There are also important anions. So the anions that we're going to be thinking about as time goes on will be chloride, bicarbonate, HCO3-, and this is phosphate, PO4-3-. Now, even though there's going to be a great difference in how much sodium is inside or outside the cells, or how much potassium there is, we're going to see that the inside and the outside, the extracellular and the intracellular fluid, will still have the same osmolarity. And this is the number you're going to see, about 300 milliosmoles. And I'll show you a graph that better explains this in a moment. So let's take a look at this. At the top, it's blood plasma. Well, remember that blood plasma is an extracellular fluid. So you could put up here extracellular. Okay, so this is extracellular, and this is intracellular. And what do we see? This very first column is sodium. So sodium is in great concentration in the extracellular fluid and is very little in the intracellular. If we look at the second one though, now we're looking at potassium. It's exactly the opposite, isn't it? Potassium is in high concentration inside the cell and is in very low concentration outside the cell. Remember that one, remember that one, remember that one. Now, chlorine always follows where sodium is. So that's how I remember this. So wherever sodium is, chlorine will also be found in high concentration, or where it's not, it'll be found in low concentration. Calcium and phosphate are the next two. Now you'll see that they're found in relatively low concentrations in the extracellular fluid. Calcium is especially low in the intracellular fluid, and potassium is higher. Phosphate is higher, phosphorus is higher. But regardless of which ion is higher or lower, what we see is that both are at 300 milliosmoles. So the total concentration of solutes is pretty much the same inside and outside the cell. Now, which ions are there is different, but the total is at 300. I'm just going to mention sodium as being the most important ion for maintaining what's called the resting membrane potential. You'll know this much better next week, but the RMP, the resting membrane potential, and where sodium lies inside or outside the cell is going to be critical, again, in muscle and nervous tissue function. Sodium accounts for 90 to 95% of all the osmolarity of the extracellular fluid. So it's a major, major player here. Okay? And we'll continue to discuss sodium for the next few weeks and its importance. So that brings us to the end of this smallest little section, but I want to go to that little second PowerPoint called mass balance. And there's about 7 or 8 slides here. And just go over these and that'll finish up our conversation for the day. So this is also information from chapter 24. Now, we were talking about water balance a moment ago, and this just expands on that idea to mass balance. So not only do we have to have an equal amount of water coming in and leaving the body every day, we also have to have a balance of food stuff and everything else coming into the body. And again, it's going to be balanced between the intake and the excretion or what we leave. It's not a difficult concept. Now, when we talk about mass balance, we have to talk about clearance. That is, how fast do we get rid of molecules? Not necessarily, I'm not talking about water here, I'm talking about other molecules. So yes, the urinary system is getting rid of our solutes, right? It's getting rid of molecules. The integumentary system, we are sweating out, and in our saliva, we are getting rid of waste products. Your hair can be used forensically to determine drug use or other metabolites. So molecules are actually stored in your hair, and as your hair grows out, those molecules are, quote, leaving your body. If you've ever had a big garlicky meal, you know that you can smell that garlic because that garlic is literally being released through your breath. And defecation and the breakdown of things in the liver is also contributing to the clearance of molecules from your body. Now, a very, very important concept, and that is that homeostasis is not equal to equilibrium. Equilibrium, right? When you think of equilibrium, I hope you think, okay, everything's the same on one side and the other sides. Everything's equal. As I've already described to you, sodium is never equal. Sodium is never the same on the inside of the cell as it is on the outside of the cell. Potassium's never the same on the inside as it is on the outside. So it never goes to equilibrium. But that difference in sodium and potassium is necessary for the body to properly function, and so those differences are important for homeostasis. So homeostasis does not mean that everything is equal. It just means that everything is where it needs to be. Now homeostasis, right, is going to insist that there's an osmotic equilibrium. Remember, water is pretty much the same on both sides, because remember, there's always on both sides 300 milliosmoles. Right? So because the concentration is the same on both sides, the water will be the same. However, there will be a vast difference in the chemical equilibrium. We've described this, right? Sodium is in higher concentration outside, potassium's in a greater concentration inside. But not only will there be a difference in the chemical equilibrium, but there will also be a difference in charge. What we're going to see over and over is that the inside of cells is more negative than the outside. The inside of cells is more negative than the outside. So if I could take a little electrical probe and put it inside the cytoplasm of a cell, it would be, quote, more negative than the environment outside of the cell. And this is going to be because the intracellular fluid has more anions, more negatively charged ions, and, as we'll see in a moment, more proteins, which are also negatively charged. Let's take a look at this chart. You've already seen this at the very beginning of chapter 24 presentation, and that is, where is fluid in our body? But what I want you to see in this picture is this breakdown. It's referring to plasma and to interstitial fluid. And do you agree that those two are both, right? Plasma and interstitial fluid are both extracellular fluids. So they're clumped together here. We've already said this. There's about 65% of your fluids are found inside your cells, and about 35% are found outside your cells. Now I know that I told you that that ideal normal male had 40 liters of fluid, and I know that these two numbers add up to 42 liters. So just keep in mind that these numbers are going to float around a little bit, but know the overall patterns, know the overall values. Don't have to memorize every single number here, but have a good appreciation of the ranges. Maybe this will help you as well. So remember again that plasma and interstitial fluids are both extracellular. So again, where's sodium? Sodium is found outside, not very much inside. Potassium, other way around, mostly on the inside, not on the outside. Chlorine, remember I told you before, chlorine is found where sodium is found. Bicarb we'll talk about later, but there's more bicarb outside. And this is going to be important right now. Look what we see right here, that inside the cell there are more anions and proteins. So this means that there's more negative charges inside the cell than there are outside the cell. Again, very important. More negative charges inside the cell than outside of the cell. Well, how does the body do this? This is a flashback to Biology 105, Lab 2. How does the body maintain a different concentration of sodium and potassium and chlorine throughout the body? Well, it all comes back to membrane transport, right? We talked about this long ago, membrane transport. Remember that there are passive transport mechanisms like diffusion, osmosis, all that's over here. These are processes that do not require ATP. However, there's also those ATP requiring processes, and these are the active transport mechanisms. Active transport, remember what happens in active transport is that you are actually creating a more concentrated environment. You're putting molecules from an area of lower concentration and you are sequestering them or putting them into an area of higher concentration. To do that, that requires energy. So endocytosis, phagocytosis, all of those processes require energy, and that's the big thing I want you to see here. Just remember that we need energy to move these molecules to places where they are in a chemical imbalance. So just to get a picture on active transport, whenever you see an active transport mechanism, you will always see ATP somewhere in the picture. So ATP is being spent. There's energy being used. Now, the number one active transporter that I want you to know about right now is the sodium-potassium ATPase. You'll also hear this called the sodium-potassium pump. And what this is doing is maintaining the sodium-potassium difference. The way that this transporter works is that it pumps 3 sodiums out of the cell for every 2 potassiums that it pumps into the cell. And ATP is necessary for this to happen. So what is this pump doing? This pump is assuring that sodium is constantly being pushed out and that potassium is always coming in. It's helping to maintain this difference in the concentrations. This is amazing. This takes up about 30% of your ATP. When you're sitting there right now listening to this, 30% of your ATP in your body is going to maintaining your sodium and potassium concentration differences. Wow. That certainly suggests that the location of sodium and potassium is absolutely fundamentally critical to your overall homeostasis. Okay? So this sodium-potassium pump is hugely important. 3 sodiums out for every 2 potassiums coming in to the body. And that brings us to the end of this conversation on fluid balance and electrolytes as a way of jump-starting into our conversation about the nervous system. So I will pick up with chapter 12 and the nervous system, and we'll talk about action potentials and why this sodium and potassium difference is so critical to the functioning of your neurons as we continue forward. Don't forget to get enrolled in Connect. Don't forget to start your Connect assignments. You can certainly go ahead and do the chapter 1 question. There's just one question for chapter 1, and then there's an assignment there also for chapter 24, and you could even get started and get ahead and start working on the chapter 12 assignment. If you have any questions, please don't forget to email me. It's been a pleasure. I'll talk to you soon.